Howdy, my name is Gavin Nielsen, and I'm still looking for a good name for this channel. But anyway, it's basically it's about modeling, and we're in the middle of a Micromouse modeling adventure. So we left off last time. Well, first let me just say, sorry it's been a few months since I posted anything. I've kind of moved towns and changed jobs and a whole bunch of stuff happening. So now I'm somewhere close to settling down, and figured it was time to get a new video up. So anyway, let's take off from where we left off. We had last time finished the motor integration stuff, and this time we're going to hop in and there it is. We're going to hop in and get the rest of that done. We finished the motor, but now we need to do the gearbox and the integration. So the gearbox should be pretty easy. Remember, we basically, for the motor, we just parameterized it and parameterized it by stall torque and no load speed. Okay, so that's all good. So now we need to hop into the gearbox, and the only thing to do in the gearbox is to drop a mechanism, which will be a gearbox in there, nice and simple. So we'll connect shaft in and shaft out. And what exactly is the gear ratio? Here's that motor we're working with. The exact, or close to exact gear ratio, close enough for us, is 75.81 to 1. That's what we're going to put in here. There's the gear ratio. You don't need to change any of the incoming variables for this. That's all we need. Okay. And you'll notice it changed to the right kind of a node there. Now that Simscape and Simulink could understand, okay, that's just the domain. Let me unhook it and also show you what I mean. If I unhook that, and it doesn't know what, it knows it's a physical port, but it doesn't know what kind. So as soon as I hook it up, then okay, that's something it knows how to deal with. Okay, very good. So we've got that. Now we need to connect that to the R output of the motor. And what we're going to do is we'll make a rotational reference. So basically we'll hold on to the frame of the motor, and we'll turn it. That way we'll have something to push against on both of them. And we need two gearboxes. We need another, so that's right axle. I'll make this left axle out after the gearbox. Good. Connect right axle to right axle. Connect left axle to left axle. Perfect. We'll just leave these dangling here for the moment. We'll probably take them out. We'll take them out. There's no need for them now. They don't hurt anything, but they're not necessary. Okay. And we've already done the stuff inside the model that we need to. Here, so you can see a little bit better. We already, there's some question marks here because we need to get in and set this library to part of the path, of course. Good. So let's do a Control D, and those question marks should become unquestionable. So now we can take and make this PCB platform show only this. Zoom to that. Okay. Show the rear stabilizer and the two wheels and the front stabilizer. Okay. Good. So here's our thing. Okay. I'm going to do another update. These should question marks should go away, but they don't seem to be. Why is that? Let's see. Okay. Yes, I'm in the right directory. If I hit go, do I have what I need? Yes, I do. Okay. It's odd that they're not updating. Well, anyway, I think we're okay. So before we can actually drive this thing, we also need to connect, we've got to connect our H-bridge up. And you might remember that, I'll make this a little bit bigger so you can see. You might recall that we had a bunch of logic that controlled the PWM oscillator and the H-bridge. And so that basically was our digital inputs, that was our interface, and we had A and B. So for the moment, we're just going to hard code it to forward. So A is 1, B is 0, and then we'll give ourselves a command. And the command was between 0 and 1, so we'll just start with a command of 0 just to begin with. So what we want to do, go out of this, make a couple constants. One and 0. I don't really want to see their names. Close up, and then we're going to connect the in, and we'll just connect both motors in parallel here, I think, for the moment. That's fine. Go up one level. We don't need to worry about these for the moment. They're just placeholders, so I'm going to comment them out. And like I said, I'm just going to put a constant in here to begin with, the value of 0. So if everything is working correctly, it should just land. But have to bear in mind, this is the first time we've turned this on, so we're not sure what's going to happen. So just to review, we have 0 coming in. That is driving both commands. So it should command a 0 to the PWM, which should communicate a 0 to the H-bridge, which should give us 0 volts at M plus and 0 at M minus, which should drive the motor, not at all, which should go through the gearbox to give us some more torque and go in to the left axle and the right axle through these bridges into these joints, which should help us not do anything. It should hold still. So let's try this. So if I hit start, okay. So far so good. 5 seconds. Okay, what happened? So the time of the simulation was 5 seconds, but for some reason we only got to 0.22 seconds. So there's only one reason, and we actually didn't have an error. There's some warnings here, but no errors. So probably we hit one of our stops. Remember, we had some stop simulations if the current went above 1.5 amps. So I'm going to put a scope on here, and I'm just going to see what was the current that came out. And I'll hit run again. Okay, we got to about the same place. All right. So this one started spiking, and it got to about, yep, went past 1.5, headed to 1.6. So that's definitely what's going on. So that means that there are, well, there's at least one thing wrong, and I'm thinking about the way we parameterized our motors, and we didn't actually include anything that talked about how much current they drew. So let's do this again. Let's hop into our motor 2 model. Here it is. And I'm going to grab, let's see, I'm going to grab the motor out of here as it stands and go back to this. I'll save this as motor 3. I'm just making another model to analyze what we need to on here. Delete the motor that's in there, put our current motor on the block. Now, so here's our thing. Our speed, we could let this settle out a little bit more, 20 seconds. Our speed would get just over 30,000 RPM. Our torque, well, our initial torque, which you can see here, was around 18 E minus 3 pound force inches. So that's all good, but we didn't really set up something to monitor current. So let's do that now. Current sensor. Remember, that's got to be in line, so let's put it in line. All right. Control R's to rotate it around. Change the units to amps, and we will put a scope on that. Call it current. We'll call this signal current. Okay. Now, here are those scopes. Let's hit go again. See what our current does. Okay. Well, our current isn't terrible. It's about 1.1 amp. But it's actually still not correct, because if we look back at that data sheet, our stall current is 1.6 milliamps. Excuse me, 1600 milliamps, so 1.6 amps. So we've got to correct that. So let's get this motor right. Let's get in here and change the parameterization and change this to be rated power, rated speed, and no load speed. So we'll leave the armature inductance alone. The no load speed hasn't changed, but we're going to set our rated speed at a rated load to something different. So I'm just going to kind of go right in between. Just as a reminder, I did a little spreadsheet here just to remind you of a couple of things. So this is torque speed curve. This is speed in RPM on the bottom, and our torque in pound inches on the vertical axis. But this is power, okay? And you have to bear in mind that about halfway between on the torque speed curve is the maximum power. That's where you get the most bang for your buck if you're trying to extract the most power out. So that's because of the fact that this is we're assuming it's a linear model like this. We wouldn't have to pick this point, but I'm going to pick this point. Just I think it's good form. So anyway, that's about 15,000 RPM. Okay, and then I want to give it a rated power. We know that at, let's pull that back up again, at 1600 milliamp, at 0 RPM, we pull 1.6 amps. But at 0 RPM, we don't have any power at all. We know that we have some electrical power going on, but we don't have any mechanical power. So that electrical power is 6 volts right here, times 1.6. So you don't have to listen to me do math in my head. 1.6 amps times 6 volts, that's 9.6 watts. So we know that it's going to be less than that. But we don't actually know what it is. So we could go back and calculate the power like I did here and see what should that be. But actually the model, we also don't know the other assumptions the model's making, which we could dig into a little. But in the interest of time and practicality, all we really need is to adjust this rated load output so that the output at stall matches the datasheet, because the datasheet doesn't get into anything in between. So for us to get into all that the model assumes in between is interesting and good to know if you know what's going on, but otherwise sort of pointless. So what we're going to do is we have this current monitor here, right here, and we want to adjust it up until we see 1.6 on that. So let's start at 9.6 was the max. Let's just try 6 watts. I know it's going to be less. Say OK. And then run. Okay. So we can see, let's see, get it so you can see everything still. We can see that the current's about 4 amps now, so too high. Let's cut that in half and say, what if it's 3 watts? We'll run that. Getting closer. So now the current is 2 amps, but remember we needed to get it to 1.6 at stall. Oh, I'm sorry, we also need to put the model in stall condition, don't we? And that's easy to do. We'll just take a reference and connect that to the output. Very easy. So now when we hit run, our speed's 0 and our current is maximum, so that's our stall torque. So let's go back in here, and now we're at 2. How about 2 watts? Now we're about 1.4, so now we're a little bit low. How about 2.2? A little bit low. So how about 2.4? It's looking good. Yeah, that's pretty close. Okay, but there's one other condition that we need to match. So that's stall torque, stall current. But what about no load current? So let's comment this out. And we'll give ourselves 20 seconds. So now we want to know what's the last, here, I'll do it this way. What is the last current that we see? And that should be 120 milliamps. If we look back at our data sheet here, free run current 120 milliamps. So that's what it takes to push the whole thing. So how do we get this into the model? Well, there's one other thing we can do. If we look at the parameterization of this, we have a rotor damping parameterization. And this is currently by damping value. but we can change it to by no load current. And so we want our no load current to be 120 milliamps at 6 volts. Good. So now, if I run this, hit escape. Man, I hooked this up to the torque. I meant to hook it up to the current. There we go. That's exactly what we want, 0.12. But now, if we look up here, we can see that our stall current is wrong, so we just need to make a little adjustment. No big deal. So we'll turn this back on to lock ourselves into a stall and hit go. Remember, we want to get this at 1.6. We're about 1.7 something now. So 2.2 watts and go. That's pretty close. I'm going to say that's good enough. We're pretty close to 1.6 amps. Okay, so now we have a motor that's good enough. So I'm going to hit save to our motor 3 little test bench here and go back to our original model. Where did you go? Here you are. Here's the motor we want. So we'll put that in. Reconnect all these guys. Okay. So, we still have these guys stopping if we get above 1.5. Let's actually make this, we made it 1.5 because of the amplifier it was connected to. It was limited to 1.5, but we may get to 1.6 because of that's the way the motor's parameterized for stall torque. So I'm going to set this to 1.65, and in the design we may have to do something different if that's a common thing if we really get to stall torque all the time. But there's no sense in stopping the simulation because of another design consideration that's not really relevant to the simulation. So all right, so we got that. So let's save it, and we'll go to this and hit go. And now we stop at 0.14. Remember, we have this set to go 5 seconds, so we're still getting above the target current. And if we go look at that, we can make sure of it. Yeah, we're getting to below negative 1.6 or 1.65 amps. Why is this? Because remember, the motor command is 0. We're driving it with the 0. Well, we've got to remember too that we're working in SimScape, and SimScape is bidirectional. And so even though we're not giving it an input command, we are engaging the tires, the wheels, in a collision, which is going to generate a current just like a generator or an alternator would. Even though we're not giving it a current, it can generate its own current because of the mechanical motion. So why is that? Well, the reason it spikes like that is actually because these joints that we're connected to don't have any damping. Let me go into one of these. Remember, here's our bridge 1 left axle and the right axle bridges. They're connected up to these joints, and these joints right now don't have any internal mechanics. There's no stiffness at all. So during the collision, the axle can turn effectively infinitely fast, which of course generates a spike in the electromagnetic field, which generates a high current, which is what we're seeing. So all we need to do is add a little bit of damping to this, and I'm going to put in 1 e minus 3 Newton meters per degrees per second, just so that we have a little tiny bit of damping. So that way there's some mechanical resistance so that the speed at which that axle turns isn't so fast that it won't generate an electromagnetic field such that it increases the current beyond our bounds. Okay, so I did that, and now I will save that and go here, hit run again. Oops. Simulate. Okay, this is looking good. Looks like we've collided with the ground and we're just sitting there. And that's all we wanted to do, right? Because we got to remember, good, we got the time 5. Now we haven't actually given it a command, so we finally have stability. We kind of have to fight tooth and claw for stability here. Now it's time to give it a command. So I'm going to go for broke and give it a command of 1. Remember, 1 is 100% command. And we'll go back to, we gotta watch this. And let's simulate it again. I'm gonna zoom out a little bit. Well, I didn't like that because I think there was a jump in current, I'll bet. Let's double check and see. Yep, there's a jump in current. So the combination of our dropping it and our giving it a step command put us over the edge. So for the moment, I'm going to comment this out, the stop simulation part of it, because I think that's going to pass, and I think we learned a lesson that we needed to learn there. And now let's look and see how this works. All right. So there we have it. It hits the ground running, literally. Let's see. So I'm going to back it up. If anyone from the MathWorks is watching this, please improve your rotate commands because this is a pain. Okay, so if I hit play, and I'm going to slow it down just a little bit, so maybe 1/4 speed. You can see it hitting those bumps. Okay, and I'm actually going to stop it there. I don't like the solve very much. I want to make sure that my max time step is 0.05. I don't want it to take bigger steps than that. Okay. You can see it bouncing back and forth on the stability wheels. And there we have it. We've got a nice looking little Micromouse that's got full power, and we're giving the same command to each side. This is something else useful to think about. We're giving the same command to each side, and we are indeed going in a straight line. So we're doing something right there. That's good. All right, this one got kind of long, but that's sometimes the way system integration goes. You got to walk through those problems and figure them out. So I hope you enjoyed it. Like it, subscribe, and give me accolades. I don't know how else that works. Send me money somehow. Not sure. Yeah, but I hope you enjoyed it. Come back and see me soon. I'll talk to you later.